Okay, let's
So,
get started.
morning, everyone. So today I'll be discussing about modeling in science, mainly about phenomenological versus mechanistic modeling. They mentioned this in the one of the modeling sessions in the meetings. And just to straightforward jump ahead, modeling is essentially a mathematical or computational tools, which is combined together to describe a system or data that we have collected. We have to also note that all models have their limitations and no models are 100% perfect. So using these models, we can still extract some information needed and gain some knowledge from them. So they have two main classes of modeling, which is mechanistic and phenomenological, which you can see here have their own advantages and disadvantages. So phenomenological is pretty much the model we're familiar with, like deep learning stuff, neural networks, regressions, random forest trees, etc. And mechanistic model might be one of the models that we rarely touch since we're more of the dry lab situations, I would say, and we're more of a machine learning oriented lab. But for mechanistic models, its goals are to mainly find the causal relationship between data or between systems. So it explains more how the system works and how each data can affect others' data, which, unlike phenomenological, it's more used to find patterns in data. So yeah, mechanistic model is for causal understanding. They use more of a math-based heavy. So it uses equations and simulations, and it's very common in disease modeling, immune response, and weather forecastings. So the kind of models needs the domain knowledge and some assumptions in order for we to create the equations that find relationships between each other. And for phenomenological models, it's more of a pattern recognitions and predictions, which is mostly used in machine learning, deep learning, and statistics. It learns to find patterns. It's very fast and very flexible. And but the disadvantage is it's less into causal mechanisms. So it's only for pattern recognitions, and we don't actually know how each data correlates to each other. So in mechanistic model, the data needed is more moderate as compared to phenomenological. So it doesn't need as much data as we know how deep learning needs data. The mechanistic model is good for high interpretability and good for explanations. Meanwhile, for phenomenological model, it's good for predictions and pattern findings I mentioned repeatedly. So here are some of the examples from mechanistic model and phenomenological models. So mechanistic model is the SIR model, which is based on this um, differential equations, and also there's ODE, and this is an agent-based model which can simulate data and systems to find out what's the relationship between one data points to other data points and how it affects the whole data in general. So in mechanistic model, the question is, what makes this happen? Usually used for simulations and to explain the data, but for phenomenological, the question is, what might happen next? And it's usually used to find patterns and make predictions, just like deep neural networks, regressions, and random forest. So, in relations to the meetings earlier last week, the one of the keynote speaker is talking about vignettes from coronavirus pathogenesis and vaccinologies, and the first case is about effects and efficacy, which I think we also touch the topic a couple times. So that the speaker mentioned that the general agreement that people over 75 years or ones who are susceptible to severe disease should receive a booster vaccine. This kind of agreement can be tested using this mechanistic model. So using a mechanistic model, we can estimate how the vaccination affects the spread, severity, and others. So yeah, we can use the SIR models or the agent-based model to simulate all these claims, which I think is really interesting because we in the lab we never really tried these kind of mechanistic models yet. And another use case for the same vaccine efficacy is that the speaker also mentioned that the assessment of vaccine efficacy is harder to calculate now, since pretty much most of people has got vaccinated, and compared to earlier during COVID, no one is immune. So it's much harder now to calculate how the vaccine efficacy works. So using phenomenological model, we can observe the data and make prediction based on the pattern that we find throughout the data. This data can be of age, vaccine type, comorbidities, and variants as well. Another use case examples from the keynote speakers. The speakers also mentioned that patients or who contracted COVID-19 has a neurological PASC. So they mentioned that the cilia and the OE are damaged at 6 days post-infections, but these are all tested on mice. So that since testing in humans is not ethical, so we can use mechanistic modeling as well to simulate the biological process, uh, why COVID-19 can induce anosmia or loss of smell, and why it damages the cilia and etc. And this way we can also predict the reason this all happens, why it affects the cilia, why it affects the neuron, and etc. And for the other use case, still in the same background in neurological post-COVID syndrome, is using this phenomenological model, we can develop to predict what kind of populations or what kind of cohorts will um, experience neurological disease such as brain fog or seizure and anosmia as well. Since the speaker also mentioned that people who recovered from COVID also experience neurological disease such as these disease I mentioned earlier. So it's definitely worth a try to use this kind of neural networks or random forests or even simple linear or logistic regressions to predict and see the data patterns of why this specific patients or this specific populations didn't recover from this neurological disease. And these are two of the modeling tools mentioned in the meetings. One is Pandora by Atomic Lab, and one is all of our packages developed by this team, Andreas Handel Lab. To break it down, Pandora is mostly a phenomenological model inside. So I've tried to install it in my computers. So it's pretty straightforward. It's just a Docker image and containers. And after you pull it from the Docker hub, you can instantly use it on your local machine. And there's two options here. There's some predictive. So predictive is they have a lot of machine learning models that we can try, and we can upload our own data and we can visualize them to however we like. There's Disney plot, there's PCA plots and everything, so we can plot our data, and we can also use these predictive models, machine learning models, to sort of predict and find the patterns in our data. So it also works in Windows, Linux, and Mac OS, which is pretty straightforward. And I haven't given a very deep experiment on this, but it's a pretty nice tools to have. It's pretty simple UI as well, so it's not confusing to use. But yeah, so this is more of a phenomenological model. And the other packages developed by Andreas Handel is more of a mechanistic model. So such this as model builder, it allows to build models, mechanistic models to implement differential equations and other mathematical equations. So since I'm not really familiar with mechanistic model myself, I haven't been able to try and test all of these packages here, but I think it's worth to try as well, since I think mechanistic model might be worth a try. So in conclusion, people in our lab are very familiar with phenomenological model, but mechanistic modeling are still rarely used in our lab. But I think since we are somehow focusing on causal machine learning, causal reinforcement learning as well, I think mechanistic model might be worth to learn as well, since maybe it can be some of use to us in explaining um, so, causality between our data points. And again, I just want to point that all models, of course, have their own limitations, but that doesn't mean one model is also better or worse than the other. It's just that a model is specifically used on specific data and specific use cases. Thank you for listening. Any questions?
Thank you. So, a very good presentation. First of all, thanks a lot. And then I just want to address the your comments, sort of the phenomenological model versus the mechanistic model, because although we are aware of these model, I mean, at least I'm aware of this model, they tend to be simplified. The phenomenon we observe from the real world data. Having said that, if we have some um, cleaner data, say we have data from the clinical trials, because I'm not sure whether Dr. Wu or Yu is going to find us some data from clinical trials. Say for clinical trials, all these data are cleaner, so then we should be using a simpler model to explain the phenomenon, if I can put
Mm-hmm.
it this way. And then another thing is if we only have like big data, so when you uh, attend to some other meeting like biostatistical or I mean biostatistics or epidemiology meeting, and then for epidemiologists, sometimes they only have like very crude data, so
Mm-hmm.
they don't really have the luxury to put lots of feature into the phenomenological model. So
Yes.
they tend to use the mechanistic model. But on the other hand, sometimes we want to make some conclusion by, simplify our observation. So that's also something else that I think people want or people love to have. So I'm just wondering, because we've been witness so many different type of hybrid modeling in the past. Like Dr. Wu
Mm-hmm.
just mentioned the offline, I would say offline, then online. I don't quite remember
Mm-hmm.
the term, but in one example, the WD3Q&E, I believe they use the off-policy learning first, and then use online or on-policy learning to give the last mortality estimation.
Mm-hmm.
So I would say if say we have a complicated phenomenological model to get rid of all these possible confounding, say because pretty much like Yu summarized for us last week about this deal causal tree. So the
Mm-hmm.
first stage you can use different model. It could be like deep learning, a very complicated model. But the second stage, the decision tree is chosen because it's simplified. It
Mm-hmm.
is more similar to mechanistic model. So I would say these are not contraindicated to each other, but sometimes maybe we could just borrow the philosophy from other discipline, like the distill causal tree.
Mm-hmm.
Maybe in the future we could just use this kind of concept to explain our observational data. So, but I do have some question for you is when you are browsing Tomic's website,
Mm-hmm.
because she mentioned they have lots of data set available. So I'm not sure whether, for example, in Pandora, did they just build in the software or the platform or I don't know the API or GUI? Did they provide any example data there? Is there big enough for us to try? Did you
Yeah,
notice that?
that's also one of the questions I asked myself yesterday. So I was trying this Pandora yesterday in the lab. So There's no data sets available, but I remember uh, she also mentioned that there's a lot of data sets available inside. So I was trying to find where the data is located, but it's not built inside the Docker itself. So um, I might need to find a little bit more about where the data set is located. But this is a random data that I sort of pulled from the MEDT back then. But yeah, so this is our own data set. It's not their provided data set.
Okay. Okay.
Mhm.
Just maybe just take some time to explore a little bit deeper into their website to see if there's any possible
Yeah,
place that we
of
could
course.
have data available.
Yes, for sure.
Okay, thank you.
Okay, thank you.
那因为时间关系，所以我想我们是不是用